think it's recording now. Yeah, it is.
Yeah, now, but now your sound is very weak.
Very weak. I'm gonna have to try to close the mic. What about now?
That's better.
It's better, right? Um, you know that you're excited. Your excitement about science is a bit contagious. You know what? You make other people excited, and it
Good, good. I like to do that.
I know it's have to be rewarding.
Oh, good. Okay, well, let me close my. Let me
Sure.
just close this if we're going to do the interview. Hold on. Okay. Oh, yeah, see. Okay. Oh, I like grocery shopping with you. Gonna wait. I'll do it with you. It's up to you. Hi. Okay, I'm back. Just one thing here.
Okay.
Um, just answering an email. Just one last thing. Okay. And I'm glad you're infectious. I'm just going to close this off so I don't have anything bugging me and none of that sound
Mm-hmm.
from that email coming back and forth.
All right.
Um, just want to make sure I've been away for 3 hours. Just want to make sure there's nothing urgent that from my office
Uh,
that came in me in that time. I don't think so.
your office is Arizona State University, isn't it? I believe you.
My office, yeah, I work at the University at Arizona State. I just commute.
But you're not in Arizona right now.
No, I'm only 1,000 miles away or so.
All right.
Okay, I'm gonna um okay.
You're at the house. It's not very common over here in Rio. Houses, it's
Yeah,
buildings and
okay.
buildings.
Yeah, yeah. And I will have a condo in Phoenix, but you have a house here. Yeah, I know. I've been to Rio and houses, more buildings. Yeah,
Yeah.
I have a house with all this land behind me and big
Mhm.
trees. And, okay, let me close off my computer. Um, okay, I'll get them later. Okay, good.
Good.
I'm yours. Am I being recorded?
Yes, you recorded, but I can send the video after you. I don't have to post
Doesn't matter.
anything
What's
after.
this for again?
Yeah, I'm a regular columnist for Skeptical Briefs, and Skeptical Briefs is the newsletter of the Committee of Skeptical Inquirer. It's a Center for
In
Inquiry. It's a major skeptical organization in the U.S.
in Brazil.
No, not in Brazil. In U.S. It's a print version. In Brazil, I have my blog,
Oh,
uh,
okay.
and now very recently another blog, collaborators. There's more than 200 collaborators call me in, and
So where are you
I,
calling me from now?
what?
Where are you calling me from now?
Where? Rio de Janeiro, Brazil.
Yeah, you are in Rio. Okay, that's okay.
I'm in
That's what
Rio.
I thought.
Mm.
But you say this is for the U.S.,
Yeah, I do a mixed work, so
okay.
it's somewhat awkward that my work that I do here got attention in US first.
Well, that's good. That's a good thing. Sometimes they appreciate you abroad more than they do elsewhere. I'm just
Yeah,
gonna.
exactly. You remember our previous interview, so I have done others and try to publish in something with more audience, and the editor called me in
Yeah.
for being a regular columnist, and it's published 4 times in a year. My blog and the blog is more free, so
Yeah. I'm just gonna. You're as now. I've just changed the speaker so that you're not as loud. Talk to me now for a second.
okay. It's you. Can you hear me? Okay.
Yeah, I'm gonna put you back to the built-in display audio. Talk to me now.
Can you hear me? Okay. Trying 1, 2, 3.
Yeah. Now, hold on. I'm gonna keep talking.
Trying 1, 2, 3.
Oh,
Trying one,
oh,
two, three.
oh, okay, that's much better. Okay, we're good.
Good. If you could start explaining general relativity and gravitational waves, I mean, not too much technical, of course.
Well, at the point of what general relativity is a theory of space and time, and what Einstein showed is that matter affects the properties of space and time around it. It causes it to curve, it causes it to expand or contract, and naturally, then, therefore, if a massive body affects space around it, if that massive body moves, then it can produce a disturbance in space that itself propagates out like a ripple when you throw a stone in water.
Mm-hmm.
And he showed in 1916 that such a disturbance would in fact propagate out and would be a wave, a gravitational wave, and um, just like an electromagnetic wave happens when you jiggle a charge, an electromagnetic wave, a gravitational wave is a disturbance in space,
Mm-hmm.
and that means that the properties of space change as the wave goes by. In particular, when a gravitational wave goes by, if it's coming through this room here now, the distance from my hands would get smaller in this direction, and my length of me would get longer in this direction. Then this would contract, and that would get longer again. And that was prediction he made in 1916. Of course, I think he thought it would never be observed. He also retracted it later in about 1937 because he actually tried to solve the equations for gravitational waves, and he was using what we call the wrong coordinate system, and he came up with a nonsensical answer, and he thought that gravitational waves didn't exist. So he submitted the paper actually to physical review,
Mm-hmm.
and it was rejected, and he got very upset because he'd never even been peer reviewed before. He said I sent this paper in to be published, not to be reviewed, and but it served him well because before he could submit it elsewhere, before he ended up having it published elsewhere, he and someone else realized the mistake that was in the paper, and so the final published version is correct. But for a while, he didn't think gravitational waves existed.
But hold on. His last thought about gravitational waves for Einstein did exist or not?
It did.
Did.
He realized he'd made the error, and that indeed he was right; they existed. But there was a brief time when he thought they didn't exist.
Right. Einstein made some kind of changing about the cosmological constant as well, isn't it? I mean,
Well, yeah. Well, he introduced the cosmological constant because he thought the universe was static, and he thought a cosmological constant would make the universe static. In fact, he was wrong on both grounds. Um, the universe isn't static, at which point he said it was a big blunder to have included it. But it was a big blunder anyway, because a cosmological constant does not result in a static universe. It generally results in the universe we live in now, which is exponentially expanding.
I mean, around 5 years ago, 4 years ago, we discovered the boson, the Higgs boson, and
Yeah.
it's a major discovery as well as this gravitational waves. But
Yeah.
as the news hit me, I guess the physics community is a bit more excited about this new discovery. I mean,
Well, I think it got more advance notice, and I'm partly responsible for that. Um, uh, and that I do think that caused a fact, but also everything related to Einstein somehow catches the public's imagination.
my
And the
question is,
fact that Einstein had predicted this 100 years ago, it's true that Higgs had predicted the Higgs particle 50 years ago, but Higgs wasn't Einstein.
but my question is regarding the future for science, because what I mean here, I think you've said that this is important as Galileo discovered the telescope, and
Well, this is well, the point. I think the real difference is that the discovery of the Higgs is a major discovery of something that is important in the Standard Model, but it doesn't guarantee that that there'll be more discoveries that will open up new windows beyond that. The discovery of gravitational waves was the first. The telescope just turned on. It was the first time you had a machine that could begin to do this, and we're pretty well certain we'll be able to use this over the next century to as a probe of the universe. So the potential. It's quite possible that the discovery of the Higgs and the machine that discovered the Higgs will reveal to us more than gravitational
Okay,
waves, but it's not guaranteed. But
the
it's not
machine
guaranteed.
of the rigs, but now that we know the gravitational waves, we can use it in
Yeah, we
some
can
ways.
use that.
Yeah,
And the point is, knowing that the Higgs exists, we can use it to probe physics, but we're not guaranteed that we'll be able to learn a lot more. But with knowing that we can have gravitational waves now tells us that we'll automatically be able to see a lot more about the universe than we saw before.
and what kind of experiments and what kind of ideas that we have can be confirmed or refuted using gravitational waves?
Well, first of all, we've never measured general relativity in the strong regime near an event horizon where space is highly curved. We've never measured strong gravity. Gravity's always been weak, and now the results look like general relativity applies in that domain. So we can extrapolate to the domain where space is curved and roiling like a boiling sea and not gentle ripples. And
Mm-hmm.
so it's a good test of general relativity. And of course, as we probe physics closer to the event horizon, we'll learn about the nature of black
Black
holes.
holes, yeah.
But equally important, we can use the gravitational waves to look for cataclysmic events. For example, already knowing that two black holes collided of each mass around 30 times the mass of the sun
So,
already tells us important things about astrophysics. Because to get a 30 solar mass black hole, you probably need the collapse of a 100 solar mass star. And those stars were thought to be in the first generation of stars.
mm-hmm.
So it already tells us, A, that those exist, that 30 solar mass black holes exist, but also that that over our Hubble time, over the 13.8 billion years we've been in, they can still collide. They're not so rare that they won't find each other.
Mm-hmm.
But we'll also learn more about the evolution of black holes, which may be central to understanding the nature of galaxies. So, and then of course, who knows what else we'll learn? Because the gravitational waves are a signature of any cataclysmic, massive event that happens in the universe. And as I've said before, every time we open up a new window on the universe, we're surprised. So I'll be surprised if we're not surprised.
And for example, over here in Brazil, there's been a news. I'm kind of skeptical of the news, but it said a Brazilian physicist said that this discovery can make time travel in 100 years. But
Yeah, well,
I'm skeptical because in the news it only referred time travel once after the title, and the name of the research is never mentioned. But it's a major magazine over here. It's one of the most important. So
no, I think it has nothing to do with time travel. It does mean that one can exploit general relativity in a regime where gravity is very strong and fields are very massive, which is interesting, but it doesn't tell us we'll be able to do time travel in any way. And whoever said that doesn't know what they're talking about.
I think there's other news that Kip Thorne have said that no, there's a question in the press conference in the LIGO when they
Uh-huh.
announced the discovery, and I think Kip Thorne had been asked if time travel would be allowed, and he said that he would like to, but no.
Well, actually, it was we talked about it at length in the we had an event at my university which you can see online 2 weeks before where Kip was there.
Mm-hmm. It was part of the Orange.
Einstein's Legacy, it's called.
Mm.
It was the 100th anniversary of general relativity. We talked about that, including time travel, and Kip made it quite clear that he didn't think time travel was possible,
Mm-hmm.
even though he spent time writing papers to see if it was possible.
Yeah. And what about for people that are non-scientists, non-cosmologists, or non-astrophysicists? This discovery can, how, why they should be excited.
Oh, well, hold on a second. Yeah. Well, I mean, I think the point is that it's an amazing, what we're seeing here. First of all, we're observing an event which is almost unfathomable. Three solar masses, these two black holes collide in a second. And in that second, they emit an energy equivalent of 3 times the mass of the sun. Now, our sun is going to operate for 10 billion years, and it's going to only lose, over that 10 billion years, it's going to shine because of of basically 10 billion nuclear bombs going off in its center for 10 billion years, but it's still only going to lose a little bit of its mass. But these black holes, when they collided in that cataclysmic moment, emitted 3 times the mass of the sun in energy, which is more energy than is emitted by all the stars in the visible universe during that second. I mean, so just things like that should amaze you, and just to understand those kind of things can happen in the universe. And then, as I say, it tells us a little bit about where we came from and where we're going. It enhances our understanding of our place in the universe. So, from a cultural perspective, it's part of the beauty of being human.
Yeah.
It's not going to produce a better toaster, although the technology that's used there may be useful for other things, but
It,
because it pushes the edge of technology.
it's interesting to ask how the experiment was exactly done to detect the gravitational waves.
Well, that's what's amazing. I mean, the experiment itself is absolutely amazing. In order to be able to detect gravitational waves, well, there are two arms of a detector perpendicular to each other, and if a gravitational wave comes by, one arm will get shorter while the other one will get longer,
Hmm.
and then it'll go back and forth like that.
What
And
happened
so
with time in this process? Space and time are coupled, and you're
they're
describing.
coupled, but essentially the net effect is that um, of these the net effect of this is that between two different objects at a distance, the only thing that really changes is their spatial distance. Their clocks, the clocks of the light traveling between them doesn't change.
Hmm.
And uh, it's a good question though, and it confused people for quite a while. But the way you can measure the length is you send a laser beam down this end of the tunnel and bounce it back, and a laser beam down that end of the tunnel and bounce it back. And if the if this tunnel is shorter, then it takes a little bit less time for the laser beam to get from one place to the other. Well, that sounds easy, but what you have to be able to do to detect these waves and it's amazing that this is possible, is they had to be able to design a detector that could measure the difference in length between two 4 kilometer long tunnels, a difference in length equal to 1/1000th the size of a proton.
One
So
thousand.
small that even the quantum mechanical vibrations of the atoms in the mirrors that they use are much bigger than that. It's like measuring the distance between here and the nearest star
They,
to
they
an accuracy of the width of a human hair.
they have to control for this counter disturbances that you mentioned.
Yes, they have to control for that. They have to control for many things. It's an amazing bit of human ingenuity and perseverance and technology. It's beautiful. It's literally
Yeah.
beautiful. And if you're not in awe of what they can do, then you're dead.
I am. I am this. I am.
Yeah.
But it's interesting that you mentioned about Einstein and about some things that get it wrong, and it's interesting that he's also got it wrong. I mean, his comments about quantum mechanics has got a bit of.
Yeah, he didn't believe quantum mechanics worked or was fundamental, and he was wrong about that,
And
as far as I can tell.
even if I mean general relativity is complete about its predictions has been all been verified by experiments. They're correct, right?
Yeah, well, now that was sort of the gravitational waves we knew of indirectly, but this is the sort of the last thing that aspect of its general relativity that need to be tested directly. Yes, it's right all the way.
But
But so is quantum mechanics. It's been tested so much that it's a fundamental theory. Yeah.
yeah, yeah, but it's not the final story. We know that, right?
We know that quantum mechanics and gravity don't work together. They don't play well together. At a very small scales where the quantum mechanical ideas are important and gravity is strong, the two don't go together. So we know something has to give, and it's undoubtedly the nature of gravity. But we'll see.
Uh, if you'd make a prediction to me right now, what would be the next big discovery
If I knew what the big discovery
you'd be
was, I'd
doing
be
right
doing.
now?
Yeah, exactly. People always ask that. If I knew what it
Yeah.
would be, I'd be doing it right
Okay,
now.
let me rephrase that. What you'd like to be discovered
Well,
as a
I,
physicist?
I would like to discover gravitational waves from the Big Bang. The waves that have been seen are interesting, but for me, much more interesting are gravitational waves from the earliest moments of the Big Bang, a
How
period
can
called
that be
inflation.
discovered?
What was that?
How can that be discovered?
Well,
What
we thought
difference?
we discovered them last year. we can
Like
look for
bicycle, right?
signatures in the cosmic microwave background radiation coming
Yeah.
from the Big Bang. And if they're there, they might have such a signature. And if we can detect their signature, then then we'll be able to probe the physics of the very early universe and indeed the nature of quantum gravity itself. And so
Hmm.
for me, that's very exciting, that possibility. Now, what we now know is that the detector that detected these gravitational waves is not sensitive to those waves from the Big Bang,
All right.
but bigger detectors that we might be able to follow up on this, ones in space that are thousands or millions of miles across, may one day be sensitive. And and then we may be able to probe the nature of the Big Bang.
All right. What about works of scientific disclosure for you? You have written the Universe for Nothing, and
Yeah, yeah, yeah. But what about my own scientific discoveries? What?
no, in the last interview you said that you were working something a new book, I think.
Oh
And
yeah, I'm working on a big. I have worked on gravitational waves a lot, by the way. And one of the things we did show that I'm very proud of a year ago was that in fact, if you could measure gravitational waves from the Big Bang, they would prove that gravity is a quantum theory. I wrote that with a paper on with that with a friend of mine, Frank Wilczek, who won the Nobel Prize.
Nobel Prize.
Yeah, yeah. So he and I wrote that. And we won a prize for that actually. Left the gravity best paper on gravity for that a
And
couple of years ago.
you posted recently you received a Christian Dawkins Award.
Yeah, just a few days ago, I learned that I
It's
received the Richard Dawkins Award from the American Atheist Alliance Atheist Alliance of America, which is very nice. It's gone to a lot of nice people and good people that I admire, and like my friend Christopher Hitchens. So I'll be receiving that sometime in June, I guess. But it was nice to learn I'd been awarded it. And and anyway, yeah. So and the new book is called The Greatest Story Ever Told So Far. It won't come out for a year, but so you have to wait for that story.
next year.
But what?
Next year.
Next year, yeah, it's already done, but it won't come out till March of next year. Um, because of the presidential election here, things are being delayed.
Mm-hmm.
Um, and it's a
Hopefully.
wonderful book. I'm very pleased with it. It's a story of the greatest intellectual journey humanity has ever taken, from all the way from Plato, right, in fact, to the Higgs,
Mm-hmm.
and addressing the question of why are we here? The last book addressed the question, why is there something rather than nothing? This addresses the question, why are we here?
You
And
have lecture about this, I think. I've watched.
yeah, yeah, and this builds on that a lot. Just like the Universe of Nothing built on the lecture,
Mm-hmm.
this builds. I mean, there's a lot more in the book than there is in the lecture, but
Yeah, of course.
it's a it's a nice. I think it brings and talks about the future based on what we may know based on the discovery of the Higgs. So it's nice.
Yeah.
I'm look I'm looking forward to it coming out in Portuguese and
If you're gonna come here in Brazil, please let me know. And
oh yeah, I will. I've been to Brazil a few times. I'm invited there almost every year. I've been invited to go and to be there for
but
uh,
what cities?
well Rio of course and São Paulo. Those are the two major ones.
Major cities, yes. But
I mean I've been there twice. Before I've been to both São Paulo and Rio, but I've also been inland in the up near close to the Amazon and inland at a meeting once. So I've been to Brazil. I've been to three different parts of Brazil. I love Brazil. I like it. It's been a while since I've been there, but it's very nice. I really enjoy it, and I'd be happy to go back to Rio.
yeah,
I keep getting invited. It's just my schedule doesn't really allow it.
you'll be invited for public talk, is what?
Yeah, yeah. I've been invited by both by universities and by people for a public talk. Yeah, so sometime maybe I'll be able to do it.
Yeah. Thank you very much for this time, and one more time again, your availability, excitement for science, excitement. I mean, in some sense, I mean, I'm doing this because of people like you.
Well, it makes a lot to me.
I
Means a
think
lot.
everything started with Richard Dawkins for me. I mean, it's the first book of a scientist that I've ever read, and
Oh wow.
you guys keep mentioning this and make the balls keep running. So
Well, no, and it means a lot. That's one of the reasons I do what I do. So I appreciate it. I
yeah,
really do. And I'm glad you're doing what you're doing. So good luck. Send me whatever comes
of
out of
course,
all this.
of course.
Okay?
Yeah. Thank you
Okay.
very much. Bye.
Take care.
Thank you.
Bye-bye. Bye.